Thank you. So welcome to our next OAO-James Webb Space Telescope training session. This is on image processing, and we have with us today Mari Zamani, who is going to give us a really in-depth tour of what it's like to do image processing for a living in particular. But I just want to give you a short introduction. And that's what I'll start with. So today's agenda is really just going to be starting slow, with some basic stuff that you probably already know. And then Mari is going to give his talk on visual storytelling. And then I'm going to introduce something called the NASA Astrophoto Challenge, which I think is a cool opportunity to get involved in image processing and to really practice your skills using this tool called JS94L, which I'll show you how to use in a short tutorial. Then we're going to break for 5 to 10 minutes, depending on how we are with time. And then we'll have a group discussion with just everybody here. No need to go into breakout rooms or anything. If you signed up within the last like 72 hours or something like that, you would have gotten an email from me with a bunch of questions in it to kind of prep your thinking. Don't worry about sending answers to me or anything like that. It's just to help you guide your thinking on how you want to strategically place yourself with your outreach events, to understand the work that you want to do and the people that you should be working with and what you should be doing to optimize all of those things, and how you should evaluate it. So if you don't know what I'm talking about because you registered more recently, don't worry about it. I will show those questions before the group discussion so you can kind of get a sense of what I'm talking about. And then we'll dive right into that discussion, which I hope will give you some ideas for how to bring all of this into your own communities. And then I'll do a recap of all the resources that we've talked about, both in my presentation and in Mari's presentation as well. And then I'll do a quick wrap up and talk about our future plans for our next workshop, which will be in the middle of January 17th, I think. So very briefly, just to introduce ourselves. I think most of you are familiar with me by now. My name is Kelly Blumenthal. I'm the Deputy Director of the Office for Astronomy Outreach. I moved here to Japan very recently, and I've kind of gone back and forth, maybe too much, between here and the United States since then. But I'm here with my dog, and we're here for the next 3 years, and we're really excited to get to know the community and to hopefully get to know the language, although it's hard. So thank you all for being here and being excited to learn about image processing. And Mari, do you want to introduce yourself just a bit?
Sure, thank you, Kelly. So I'm Mari Zamani. I'm currently based in Moosburg, near Munich, Germany, and I help a few international organizations with their visual production for public outreach, including European Space Agency with James Webb Space Telescope and Hubble Space Telescope. So my journey in astronomy started when I was just a kid and saw a total solar eclipse completely by accident on the way to another city. And for a few years after that, I tried to convince my family that astronomy, what astronomy is and how they can benefit from sending me to study astronomy. So my first outreach program was my own family, and then ever since I've been doing outreach for the last 30 years, and yeah, glad to be here.
Great, thank you. So let's just dive right into it. So I'm sure you all are familiar with images like this. Really beautiful, stunning images that come out of telescopes in general. Probably something from a ground-based telescope would look as beautiful. But space-based telescopes produce these really incredible images. And they image processors like Maddie spend a long time learning how to process these images properly, put them together, and stack them and do all kinds of image magic to them that makes them look so beautiful. And they really do take your breath away. This image, when I first saw it, literally took my breath away. My question to you that I'd like some, answers from you about is, why do we create these images? What purpose do they serve? What are they actually doing for us? Maybe scientifically and just socially, culturally. You can raise your hand or you can just unmute yourself and start talking. There's very few of us here today, so. In the chat, maybe? Inspire curiosity about the universe, for sure. They make people want to learn more about what they're seeing. Absolutely. I think that's a really important part of creating these images is inspiring people to want to learn more about astronomy and to be curious about the world around them. I think that's a really important thing. Does anybody else have any other ideas about why it's important that we spend time learning about image processing? Or rather, why it's important that we create these images in general. Yes, it's very great in schools, definitely. It's certainly useful for outreach in particular, whether you're going to a school or teaching a class or doing some kind of event at a library or a planetarium. These images are really, really great for that. Does anyone want to talk about what they might be useful for scientifically? Maybe in the interest of time, I'll just give my thoughts. Yeah, absolutely, Tomita-san. So anyone can really understand what they're looking at just by, or get a sense for the science behind it just by looking at it. It's kind of, they're very evocative in that way. Yeah, you can help show the overall structure of some objects. I think that's a really important part because what we, I think, take for granted is that color and composition really change the way we perceive things. And it'll shape the way we understand data by colorizing things differently. Creating these images helps us accentuate different scientific processes that are going on within a system that we're looking at, whether it be a nebula, a protostar, a galaxy, or anything like that. So yeah, it really does have function, not just aesthetically, but also scientifically. And that, I think, is an important point to drive home. So I'm going to continue on in our journey. And I'm going to talk mostly about the James Webb Space Telescope, or JWST, but all of this information, really most of it, can be applied to all space telescopes, and often just all astronomy observatories in general, whether they be in space or on the ground. So JWST was launched Christmas Day last year. I'm sure many of you remember that day. And since then, it's been making what seems like constant headlines. Many people call it the successor to Hubble, not just because of the breadth of science that it can do, but also because of the really stunning images that come out of this telescope, and have been coming out of this telescope since its launch. But one big difference between the Hubble and the Webb is the size of the mirror, or rather the mirrors in the case of the Webb. So on the right here, you can see the size comparison between the two telescopes. JWST has a much larger effective area of its mirror, which means that it can more significant capture much more light than Hubble can. And more light means that we can see fainter things. We can look farther deeper into the cosmos, into the early universe, and we can do so with a much higher resolution than we could before. Now, every telescope has a target wavelength range that it is optimized to see. The Webb ranges from visible wavelengths to the mid-infrared, which you can see on the bottom of this image here. Now, the wavelength range itself is determined by the way the telescope is constructed, which includes what the mirror is made out of, what it's coated in, and then also the way that the light enters the telescope, and also the instruments on board. Now, Mari is going to cover the different instruments on the Webb, so I'm going to skip over this for now. But each of these instruments functions as an imager. And all of the ones that have kind of a camera symbol in their little infographic here will have a set of filters that allow us to isolate different parts of the electromagnetic spectrum. And in case you're not familiar with that, let me just give you an idea. So if you imagine that we're taking like a white light image of the sun, and you can pretend that this is a white light image of the sun because it actually isn't. So what I mean by white light is that there's no color filter added. You probably have some kind of filter that blocks out maybe 99.9999% of the light so that you can look at it safely, and you're not going to burn out your camera by doing so. But you don't have any color filter over it. And then let's imagine you take this image and you also take a spectrum at the same time. And you have this very characteristic graph. We call this a black body spectrum. And basically what it shows is that there's a peak of light. For a lot of stars, it's somewhere near-ish to the visible spectrum. And then it kind of tapers off farther toward longer wavelengths. So we have wavelength on the y-axis and intensity or amount of light coming out at various wavelengths on the, wavelength on the x-axis and intensity on the y-axis. So it will look something like this for this star, and for almost every star that we look at is going to have a characteristic curve like this. But if we place a red filter, for instance, over your instrument, you are only going to allow red wavelengths to go through and hit your sensor. So your image will appear more red, as we can see here. And your spectrum, you're only going to see the red part of that full spectrum that we had before. And if I toggle back and forth, you can see we're only seeing a small chunk of the spectrum, the full spectrum that we had before. The same is true for a green filter and a blue filter. Really, any filter we have will produce something similar to this. And we can flip through these kind of back and forth. And it's easy to see how these filters will isolate different parts of the spectrum. And if we were to stack these different filtered images on top of each other, we would get back the full white light spectrum and the full white light image back together. And we'd get something that's similar to a true color image. And that is, in essence, very top level, not getting super into the weeds version of what we do with image processing. We combine images from different filters to highlight different features and bring out interesting scientific components. Images that bring together red, green, and blue filters, or maybe just two of those filters, are often called true color images. But we don't necessarily need to be limited to those 3 filters or to combining only 3 images. The professionals can create these images and they'll often do so using filtered images that are from across the electromagnetic spectrum, as we can see here. So in this image here, we have radio, infrared, optical, ultraviolet, and X-ray all coming together to show us this image of a nebula that maybe we're all kind of familiar with. So the last thing I want to point out that I think is kind of important when you're talking about astronomical data is that astronomers almost always use the FITS file format. This is both for historical and for practical reasons. FITS files were built for astronomical data, and they're really very flexible when it comes to data storage. Not only that, but they're a much higher resolution and contain more information than regular JPEG or PNG images. Now, don't worry if you have never seen this before. It's pretty easy to get used to. Like anything with tech these days, the more you play around with it, the more familiar you'll become, and it'll become kind of like second nature after a certain amount of time. So I'm going to stop here and hand it off to Mari, who's going to talk to us about visual storytelling.
Thank you, Kelly. Share my screen now. So to take it up from where Kelly left it, we want to look into how the James Webb Space Telescope images for public outreach are produced, how those nice, colorful images that you see from James Webb all over the news are produced. For that, we first need to start with the journey of the light itself. But don't worry, it won't be all the way through the journey, just the very end of it, where the light reaches the instrument in the telescope and ends its sometimes billions of years of traveling. So where the light ends in James Webb instruments exactly, so after the light enters the telescope, then through the secondary mirrors and all the other auxiliary mirrors, it will go through different instruments. This is, for instance, how the light enters through MIRI instrument. MIRI is mid-infrared instrument for James Webb, which is sensitive to mid-infrared light. So you can see the light here colored as blue, going through different mirrors and then going through a filter from the filter wheel, and then at the end ending up on the sensor of the mirror. So the filter wheel, of course, can change the filters for different observation, for different purpose. And this, of course, is for MIRI instruments. Other instruments can have different capabilities and different components to let them have bigger filters or let the light to travel much less inside the instrument. And once the light reaches the sensor, it produces an image. These are, of course, all black and white images. These engineering images that you see here was first captured to fine-tune and then just colorized to orange for outreach purposes. But These are some of the very first slides that James Webb saw after its final fine-tuning. And you can see here some of all the primary instruments on board of James Webb telescopes can produce some kind of image. They also can produce other things, but even the spectrograph, the near spec, which is designed for spectrography, can produce images, but producing that images is not as easy as taking FITS, downloading ready to go FITS file from the archive. It takes some scientific doing to post-process and produce an image from the spectrography data. But the primary imaging instruments on James Webb are a NIRCam, which is in the center. You can see how the field of view of you can see the field of view of NIRCam compared to other instruments, and it's actually has two sensors working in parallel, and it's sensitive to near infrared part of the light spectrum. There is a parallel other imaging instrument called NIRIS, which have the same characteristic as a single NIRCam sensor, but it can be used in parallel with other instruments to study a parallel field while other instruments are observing the central field. There's 5 guidance sensors, which are just to make sure the telescope are in the right course and there are minimal movements for sharp observation, and the MIRI instrument, which is sensitive to mid-infrared light and is a collaboration between European Space Agency and NASA and some universities in the US. So, okay, so now light reaches the instrument. Now we have an image. Now we have a series of digital information that we can translate into image. So what happens then? What happens after that? Here in this slide was first produced for WST, it's a survey telescope in Chile for European Southern Observatory. Basically, the process shown in this slide is true for almost every telescopic images produced by professional observatories and organizations in astronomy. And there could be some differences in the methods in different level of each process, but primarily they're they have the same basic. So first light reaches the sensor, and then we have the raw data, what we call raw data. Usually people don't encounter raw data, even if they think they do. For instance, sometimes you might take photos with a digital camera that produces raw files. But once you open that raw file, for instance, in an application like Photoshop or other image processing apps for such images, you would see colorful images which maybe have, I don't know, wrong white balance or something that you can fix, but it's still pretty nice already. the fact is that's already processed. So it's very hard. It's usually the raw data is not seen by the end user. And we can see examples of raw data for web later on. But yeah, it could be surprising sometimes for users when they see, for instance, how their own cell phone photos are actually look like at a raw format. Okay, then we go, the raw data goes through what we call a data reduction pipeline, or a kind of what I like to think of pre-post processing. And that's reduced, it creates a reduced file. What it happens is that there are different kind of processes being applied on the raw data, for instance, subtracting a flat field or a dark frame or a bias frame, depending on the instrument, depending on the telescope. This could have different, they might be necessary, some of them may not. Then in some cases, for instance, for instruments that have gaps between the sensors, as like the Omega cam, which you can see in the image here taken by the VST, to fill those gaps and also to expand the field of view of the image to capture more of the object if the object is covering more part of the sky than the original field of view of the instrument is showing. Then we take several images of that part of the sky with a bit of tilt and shift. That would help to create a mosaic. For instance, panoramas are a kind of mosaics. So you take several images and then you try to stack them all to create one image. And then after that, of course, there after that it goes through Fitts liberation, something that Kelly mentioned. We have what we call a science-ready image already in Fitts file, and then we will convert it to a TIFF file from Fitts to TIFF to go further with post-processing of a nice colorful image. So then there is balancing of the background level, where there could be some background gradients depending on how the sensor is reading the data, depending on the smallest temperature in the sensors, or for instance, in case of ground-based observatories, there could be air glows or other atmospheric effects that causing a background gradient. And after that, so they have to be removed. There are techniques to remove that, and then after that we go to cosmetic cleaning. Cosmetic cleanings could be usually is done manually and is done by experts who understand what is exactly data, what is not, and how some of those not data ended up in the image and why they should be removed. For instance, this could be could be burned pixel caused by cosmic radiation. In the case of, for instance, Hubble Space Telescope, that happens so often for almost for all images. They have lots of such artifacts usually are dramatically reduced and even gone after stacking several exposures from the Hubble, but some parts might still remain dirty, as artifact cleaner might call it. Then the process of colorizing those images taken in different filters. Again, as Kelly mentioned, astronomers are more interested to observe an object in a specific wavelength of light than having a very an image in all the light spectrums, but not with any kind of precision as it is produced on or for instance mobile cameras or day-to-day cameras. They are interested to see emissions from molecules, from elements in those objects. They are interested to see the smallest shift between the line of emission that such thing produces in different objects, and then they try to analyze that. So they need high precision black and white images produced by specific colors. For most of the work, there are some works that might not really need that. And those black and white images, we then colorize each of them and then stack them all together to produce a colorful image. And the process of how it's done will be explained later. And then, of course, the final image, the colorful image, is produced. That was the basic I mentioned. So here we go, seeing the what a raw image for Galaxy M74 for James Webb Space Telescope and MIRI instrument looks like. And this is a raw image, but you can see it's actually already stacked of 3 exposures. So the MIRI instrument is, if you remember my second slide, the MIRI instrument is something like this. And there was 3 exposures repeated with a bit of shift. And then these 3 exposures were stacked together into this raw file. This is, of course, for instance, kind of like taking a panorama. And so you might be surprised that, for instance, this is a bit different from what you might look like, what you might have seen on the media or from NASA or ESA, the images that was produced by James Webb. And the fact is, you would be also surprised if you had seen the raw files from your mobile phone camera or from any digital camera, to be honest. The raw file is actually something very raw, and it how you read that raw data or raw material is basically very important. That's why almost very, very limited number of users see what the raw file of the product they're purchasing actually looks like. And of course, data reduction would help with finding a way through this raw data to extract those parts that are considered data, and to limit or completely reduce those parts that are considered artifacts or a part of the instrument artifacts affecting the image. And this is also in a great significance depending on how you read that raw data. It's not that you're actually removing something from the image all the way. Most of the time, it's about how you read that image properly. So after the image reduction is done, it looks like this. So we just go for a before and after again. This is before, this is after. And luckily, this data reduction is applied on all of the JWST images that are published on the Science Archive for the public. So we call it calibration level 3. And so they're fully reduced data like this. And you can start with those already processed. So even astronomers working with James Webb mostly don't really see this image. They start working on this image, what is we call science rating data. So after that, we apply some sharpening and noise reduction. This is a crop of the bigger part of the image that you saw in the previous slide here. And sorry, this is not the sharpening part. This is the part that we remove any background gradients or kind of level the background. So for instance, you see here in the right part of the image, you see the level of black is different to the left part of the spirals of the galaxy. But here there is a balance between the left part and the right part. So that's applied in this part of the processing. And here, a sharpening and noise reduction applied on each filter, so you can see it before and after. And then we come to colorizing. You see, what you see here is the Orion Nebula as it's seen with VLT telescope in Chile, also a ground-based telescope. The basic of post-processing of a color assignment or colorizing the astronomical images is the same as this image. So we have a filter taken around the wavelength of 500 nanometer, another filter taken around the 550, 560, another one around 625 nanometer. And these actually pretty much correspond to the part of this spectrum that we perceive as colors blue, green, and red. So these are those filter that is, for instance, 475 nanometer is will be colorized as blue, and the 625 will be colorized as red. The highest number will be colorized as red, the lowest number would be colorized as blue, and the middle one as green. In this case, this is, of course, the same colors that human eyes would have seen, because the filter exactly corresponds to colors as human eyes would perceive. This is called chromatic order. So colorizing the filter with the lowest wavelength, blue, and the highest one, red, and the middle one, green. This is called chromatic order, and it's the primary method of color assignment in our line of work, and this is how most of the optical images are colorized. Most of the optical images that are produced by professional observatories are produced, and I mean, for public outreach. And then, but of course, this is not the only way to colorize. It's not the only method to colorize those filters and turning them into a colorful image. But this is one of the main ones. So I want you to have this in mind when you want to, for instance, create an image, a colorful image for yourself. This is the chromatic order. This is probably your best friend and way forward. But there are other ways that we would also explain later. So, okay, you might ask, what's wrong with astronomers? Why they cannot use a colorful, already colored image in the device, like any other human beings, you know, images already colorful from the camera or from the phone that they produced it, why they cannot use such images, and why they had to invent this kind of colorizing methods. The fact is, actually, this is not a very new method. This is actually as old as color photography. It's about 160 years old method, and the very first colorful image produced was created with that method. And to be honest, most of the color images that you see, almost all the digital color images that you see around your life are produced with that method or based on that method. So, for instance, for this particular image, the first thing was done was actually pretty similar to what astronomers do. The photographer tried taking 3 different photos, black and white photos of the same ribbon, but with 3 different RGB filters. And then he developed those films and projected into a screen and put those filters on the projector. So they would, the color is actually added back to that image. And those projected images produced a single colorful image for the first time. Colorful photograph, I would say, would be more accurate. So what it would look like for colorizing web data. Here it is. So that's M74 after colorizing 4 filters from mid-infrared that was produced. And this is after those filters each adjusted in different ways to have a better balance in different tonality. So, okay, we took a trip into how colorful images from web is produced. Now, where can we get the data? So usually it might help you to see where we do get the data, where the international organizations that are releasing those images are getting the data. The first thing option is to get the data from the principal investigator or the scientist who proposed that observation in the first place. And they have, right now they have, most of them have proprietary access to that data, an access that the public cannot have for another 6 to 9 months, depending on the data. So they come to us, they say, okay, this is the observation I made with James Webb. I think it will make a nice story with the science I'm producing, or I think it would add more to my science if you produce the colorful image. So then with the collaboration with the scientists, we produce a colorful image that is actually most of the time end up in the even the papers of the scientists that proposed the collaboration. And the second option is that we go into the science archives and the science archives of James Webb, and then try to find an observations that are made public. I think around 15, if I'm not mistaken, around 15% of observation in the first cycle of James Webb are already public. That means in the first year, there are the observations that are made with the James Webb are about 15% of them, I think, is public already. And the rest will be public after 6 months. 6 to 6 months. And eventually all the data would be public. There is just this proprietary time that would allow the scientists proposing those observations to have a bit time to produce their science. So we go into those archives trying to find objects that are visually appealing. They might not have produced a specific science or very particular science already, or the scientists might be still working on it, but the image is very nice and we want to share it with the board. This is something that you can do too, and we'll talk about that later on. So the third option is that data that we get by proposing our own observation for public outreach observations. This is coming from a program for Directorate of the Telescope of the Science. There is a designated time for the directorate that you can use for different kind of observations. Sometimes it's used to produce colorful, nice images, like for instance, Pillars of Creation for Hubble or James Webb, or the early release observation, the very first colorful images of James Webb that you saw. This doesn't mean those images will not produce science. They actually did. I mean, even the first images of the first slides of James Webb, and also even the Pillars of Creation, they all produced science, but the primary objective to propose those observations were rather to create colorful images to engage public. So, okay, here's 2 places that you can easily download public data for James Webb. The first one is moderated and created by Space Telescope Science Institute, and it also includes in 2025 other telescopes data from 20 something other telescopes. So you might want to filter through those for James Webb images in particular. The other one is a service by ESA, and the ESA one is designated just for the James Webb data. So you can go to the science archives, look for search the name of the object you're looking for, and try to find the observation by Webb if it has already been taken. So we know Webb, of course, sees the light in infrared, and infrared is a part of the light that is not actually even close to what human eyes can see. And even what we call optical light is not all that human eyes can see. Human eyes can see a very specific part of the optical light we call visible light. And so basically the colors produced in the images, particularly for Webb and for infrared telescopes, those are not real colors, not colors as human eyes would have perceived, because human eyes is not sensitive. And if it was sensitive with the current sensitivity in our neural links, it would most likely end up red. All of the infrared light, it doesn't matter what the specific part you observe. But nevertheless, we cannot see it. And therefore, these colorful images are mainly designed to show scientific aspects of the objects, of the astronomical objects captured in those images. We will talk about a few examples of that later on. So, but okay, then what can human eye really see? That's actually kind of important in most of the conversations I ended up having with people asking me, what's this colors all about? When I engage with discussing with them what they mean, they usually end up actually finding it very difficult to understand that human eyes is not actually or a very standard instrument to observe light, and it's actually not that much sensitive when it comes to, especially when it comes to darker situations. It cannot see colors at darkness. It only can see a visible light, which is a very small percentage of the total spectrum of light. It's even invisible light. It's not as much sensitive to red as it is to green or blue. And we know, for instance, 5% of, around 5% of populations don't see the colors as they're as the rest of the population does. They might see fewer colors or sometimes even a bit more colors than the average human eyes. But we are not actually also sure that what human eyes, average human eyes can see as, for instance, color orange would be the same color orange that another human eyes can see. They could both be seeing different things. They call it orange, they both call it orange. They know this color in their head, image produced in their head corresponds with the word orange. But is it the exact orange that the other one can see? We actually don't know. And so it's there is no accurate reference right now in what human eyes exactly see as colors. And the other thing that is particularly important in astronomy is that human eyes are actually not very good instrument in collecting too much light to increase this visibility of low surface brightness objects. Surface brightness is a specific thing that is highly important for observations in astronomy. It is when the amount of light it's the relation between the amount of light emitted from the object and the part of the sky or the area of the sky that the object occupies. So let's give an example. For instance, you see Andromeda galaxy. It's I think around 3 degrees wide in the sky, and in a very dark situation and under dark night skies, you can see it as a very faint galaxy, as a faint cloud in the sky. But you don't see any colors of it. And okay, so many people might ask you as astronomy educators, okay, what will I see if I were standing next to the Andromeda galaxy? The first thing is, of course, standing next to a galaxy is not really an option, but let's say if you were in a close proximity to take Andromeda, or even if you were inside Andromeda, you wouldn't still see any colors. This is true for most of the celestial objects except bright objects of solar system or the planetary bodies or other things. But for galaxies, for nebulas, this is true because yes, you will go much closer to the object, but the object will cover more part of your field of view or more part of the sky, and you would still get same amount of light because the object has expanded in your field of view. So this is called surface brightness, and it doesn't change with distance. So most of the objects, the colorful nebulas and the things that you would see, for instance, even if you are in a nebula, you might not really easily notice you are living in a nebula, unless with specific telescopes or other superhuman visions. you might be able to tell that your planet, for instance, is in a nebula. So yeah, that's important things to remember in discussions about colors in astronomical images. So what about colors in web images? First, let's start with how the stars would look like in web images. We talk a bit about the black body spectrum. This is actually one of the very important thing for us to understand what kind of stars emit in how much emits light in what part of the spectrum. And most of the stars go quite dim after as they go toward the visible light to mid-infrared. They are still quite visible in near-infrared, but as they go to mid-infrared, the black body emission reduces significantly. That means they become fainter and fainter and then almost invisible. This is actually also helpful because then this is where, for instance, in galaxies, we get lots of dust and gas heats, much colder than what you would see in near-infrared or optical light. So why that's important? That's because then you would know, for instance, as you see here, this is a galaxy in mid-infrared as seen by MIRI, same galaxy as seen in near-infrared by NIRCam on James Webb. And after both MIRI and NIRCam data combined, this produces the final image. So you see here, the mid-infrared is producing data that help us better understand the dust structure in and around the galaxy. The near-infrared is helping us also with about the stars in the galaxies, but also with some part of the dust and gas, and some part of the stars where might have been quite invisible in the optical light. And combining them both would give you a more complete view of the object. And so, as we talked about the black body spectrum in the previous slide, and you see the stars in the local universe appear more rather bluer than the optical light images that you see from Hubble. And that's exactly because of the graph I showed you, the emission drops in near infrared and dropping down all the way to mid infrared. So this is the same galaxy in optical light. You see the dust is blocking some of the stars, and you can see how different you see the image here. You can see the dust that is actually blocking light here. It has an emission in mid-infrared, and that's here you can see that emission and how the temperature of that area changes as these two galaxies are combining in a very beautiful dance.
Hey, Mike,
Yeah.
could you wrap up in the next 10 minutes?
Sure. Okay, this is pillars of creation as going from Hubble optical to NIRCam in near infrared. You see more stars in the background because we are peering through the dust of the nebula and the gas and the dust of the nebula. But in mid-infrared, most of the stars turn blue, but you have a better structure of the dust in the nebula, of the gas and dust in the nebula. Sometimes we color assign images based on the emission line of an element or of a molecule because we want all the colors. So we want the scientists to say, okay, the color orange you see in this image is hydrogen. The color blue is oxygen, and the color cyan is neon. And this helps people to also better understand and also better understand what they're seeing exactly, and also the scientists to better explain their science to other scientists as well as the public. So that's why, for instance, if there is an emission line in oxygen in different part of the spectrum, we won't then be using the chromatic order. We assign all the filters of the specific oxygen emission to all the filters from hydrogen to orange. So, other thing is grammar. This is more art part of the image post-processing. Many people might really ask if post-processing astronomical images is more science or art. My answer is that's why it can't be both. It is kind of both if someone from astronomy background would want to enter the field. I always advise them to take the first year courses in art schools, at least maybe some of them that are about composition and about colors and how they can represent different things. The composition primarily is one of the most important things that help us to communicate better with the public. Then comes the colors, and colors can represent different things. For day-to-day life, humans perceive color blue to be connected to cold, color red to be connected to hot. But in astronomy, it's completely opposite. For instance, we know the bluer stars are hotter stars, the colder stars are redder stars. So this is actually one point that needs to be better communicated in the description of images or while explaining astronomical images to other people. And this is something that is actually also helpful in color assignment, some of the images. Other thing is that colors can work as visual cues. They can help you actually try to construct a 3D model of the image, a 3D for the image in your head to better resolve the image, to better understand the image. And we see an example later on. And colors can, of course, spark feelings. So this is, for instance, an example of a total solar eclipse or the sea observatory. One thing that you might see in this image is the color blue in the mountains far in the horizon. First, let's talk about the other cues in the visual cues in the image. You see the first thing the human mind try to resolve in the image is a depth. Even if it's a 2D image put on a display in front of you, you know it's a 2D image, but your mind wants to extract the depth of the image. And usually that happens with different things. For instance, if I ask you, how would you say something is closer to you in this image and something is further away, you'd say, okay, the first thing might be the perspective. The buildings of the observatories in here are smaller than in here, and the perspective of the buildings can help me see that this part of the image is closer to me than this part. The other thing with the colors, our minds are trained to think by this visual cue that uh, that the mountains that are further away in the horizon in a scenery, landscape scenery, are often more toward color blue. This is, of course, because the sunlight, as the sunlight travels through the Earth's atmosphere, it scatters, turns it more blue, and the further away a mountain is, there is more atmosphere between you and that mountain. So the mountain turns to more color blue from your perception. But the interesting thing is, the mountains you see here are actually not blue. If I measure the colors of the pixels that are in here, it is dark gray. They are set to gray. So why can we see a slightest blue? That's of course depends also on your display, but if you see the blue, that's actually your mind playing tricks on you. Because you are used to see the bluer color in that part of the landscape scenery. You're seeing that. And of course, the orange on top of the horizon is also helping it by producing a white comparison color for you. The other thing for the visual cue is, of course, fading and haze. You see the mountains to the right are hazier, so you might say, okay, these are further away in my experience. But the fact is, the mountains to the left are much further away than the mountains to the right. So this is also another thing that we can perceive in a wrong way based on visual cues. But these visual cues, this is one of course, very exceptional images that are actually showing a different thing than what you expect. But we can use these visual cues when you can use this, what human minds expect to see in an image, in an astronomical image, especially in color assignment like this. This is same M74 image, and the left one is optical Hubble Space Telescope. The right one is James Webb in infrared, and the one in the middle is a merge of both of them. And in this merge, you can see, to create a depth for the astronomical image, to create a depth and better connection to this image, so people could perceive more details more easily or resolve more details more easily. The stars and the optical light is set to color blue, along with some filters in infrared that were primarily targeting emissions from the stars. So what you see here is a background of blue, which are showing mostly stars. The ones that are closer to the center of the galaxy are the cyan stars, and there are older, heavier stars, and the one in the arms are bluer stars. And you can feel a depth. You can feel that this is in the background, and there is a foreground layer of orange and reds on top of it, which is actually on purpose, and those layers actually showcase the dust distribution in the galaxy. And then you can see those parts, that those blue and orange red colors collide together and brighter than other parts of the spiral arms. And those, of course, are the parts that both layers collide. Those are nursery nebulas producing stars and heated by the young, the gas surrounding those nursery heated by those young stars emission. So that's merging both stars, dust, and the gas. So you can see a depth of distribution of dust, stars, and gas through same galaxy in different colors and different layers. This is, of course, not chromatic order color assignment. The order of color, the color assignment was done to produce this depth on purpose. The other way would be to consider, of course, the redshift, the average redshift of galaxies in the image that you're post-processing. This requires a study, and then basically you try to shift all the assigning all the colors as if it would the galaxies are in one local universe. And the other one is that we use colors also to give a depth, give a morphology depth to a distant asteroid here. This object here is, for instance, a galaxy clusters in making in early universe, and you can see all these emissions are from double ionized oxygen. And with the very high precision near spec, as I said, near spec can also produce images, but it would look like this, a bit blurry and blobby. But it's very precise. As you can see, it can take a very high precision, high resolution image of a very small part of the sky. And here you can see the same emission of gas, same line of emission with different redshifts, which help us to see, okay, this part of the gas is coming toward us as 350 kilometers per second. This part of the gas is steady around the object. This part of the gas is going further away toward our line of sight, and this part of the gas is going away in a much faster pace, 700 kilometers per second. So yeah, this gives you a depth, and then stacking all these together into a colorful image, you can feel that this is the bluer ones. The white is where the object exists, and the bluer are coming toward you. The red are going away, as the redshift is affecting the emission line. So I'm going to generally skip this, but this is particularly true for post-processing any astronomical images. And the software is also part of the package that you would receive. There will be mention of, I think, more software than what is mentioned here. But generally, the fits liberation we use with fits liberator application, and then we take it to Adobe Photoshop. You can take it to Fix Insight or GIMP if you are looking for free software or other part of the post-processing. There is, of course, JS94L that we'll discuss later on in this workshop, how to use. So yeah, and the final thing is that while looking at James Webb images, while looking at astronomical images, you could see different things. You can see a light coming from billions of light years away. You can see colors coming, different colors, meaning different elements, different chemical compounds, different scientific meaning getting translated through colors into an astronomical image. And that has been personally helping me a lot to perceive the world around me and in my day-to-day life. And I think that vision, that help that we're getting from this could also help us to better understand the area surrounding ourselves. For instance, why the vegetation on our planet are green, why the mountains in distance are blue. These are things that we could easily also see in astronomical images, and maybe sometimes even explain better astronomical images. Then it would help us in the life as we have it already. Thank you all, and feel free to contact me if you find a nice images from James Webb Science Archive and post-process it yourself. Thank you all for bearing with me.
Thank you so much. That was great. So we're going to take a break. We'll have some time to ask Madi questions during the group discussion if those come up. So I'm going to put on a timer on the screen and play some music. When the music stops, come on back in 5 minutes in whatever time zone you're in, and we will continue on with a kind of hands-on tutorial. So thank you all for sticking with us. We're going to go a little bit over time. I hope that's okay. If it's not okay, we will put the video of this whole thing. We'll make sure that you all have access to it, so don't worry about that. So I want to go through a tutorial of a tool called JS94L. That 4L is for learning. JS94L is based off of a web app version of a tool used by astronomers. So the astronomers use DS9, which is named for the Star Trek series. JS9 is a tool that was put online for the public to use. DS9 is free. JS9 is also free, but it's web-based. JS94L is free, web-based, and very, very easy to use with a lot of scaffolding and tutorials around it. So we're going to talk about JS94L, but a lot of this information you could also bring to those other tools as well. And as I said in the chat, I am going to give, or Susanna is going to put in the chat a link to a Google Doc with an overview of the tutorial that I'm going to give today, with kind of like highlights of how you can make multicolored images yourselves using JS94L. All of the resources that were used, that were mentioned in both my presentation and Madi's presentation, and some extra resources for you to kind of get started. So don't worry about taking notes or getting everything down or memorizing anything. Don't worry about it. You'll have all of this information in the end. But before I go into this tutorial, I actually wanted to introduce something called the NASA Astrophoto Challenge, which I think is a really cool opportunity, not only for you to bring this challenge, this competition to your communities, but also to practice using JS94L and get used to creating these multicolored images. I think it's a nice opportunity to do that. So I'm going to play their no, that's not what I'm going to do. This is what I'm going to do. I'm going to play their promotional video. And this is kind of like a little bit proprietary information for you guys. They haven't actually released this yet. They will release it on January 2nd. So you have some insider info, I suppose. But hopefully you can hear it, the sound. I'm not sure how great it is, but we'll see.
Images of space can be amazing. But have you ever wanted to make your very own? NASA's Astrophoto Challenge invites you to do just that. You can pick data from telescopes on Earth and in space, choose colors to apply, and produce your very own expression of the universe. For this winter's challenge, we take you into the iconic Eagle Nebula, where huge pillars of gas and dust are creating new stars, and the hottest massive stars are eroding away emerging areas of star formation. Have you seen the recent releases of the Pillars of Creation by NASA's James Webb Space Telescope? For the first time, we invite you to make your own version of the Webb infrared images and combine them with data from other telescopes. Would you like to create a wider view of the surrounding Eagle Nebula? You can choose among several data sets that provide a broader view of the star-forming region in X-ray, near-infrared, and far-infrared light. Do you want to include data of the Eagle Nebula from a telescope that you control? You can, with the ground-based micro-observatory network. Choose colors and how they are represented in your images and combine them to create something truly unique.
Please make sure to share your image with us. Tell us about your creative choices. Why did you use the color schemes that you did? Were your choices scientific, artistic, or both?
So this is just a proposal for you. If you decide that you would like to do this, I think it's a cool opportunity. You would submit the image that you create and a short description of the choices that you make, like Amelia was saying, and submit that to NASA, and then have the opportunity to be featured on NASA's website, and then also have your image analyzed by one of the NASA scientists. So I think that's a fun thing to do. But this tool is not specifically for the NASA Photo Challenge, of course. It's for anybody to use at any time that they think is necessary. So we are going to take a tour of JS94L. There is a ton of information already online, so I actually don't need to go too in depth to give you a good idea of what's going on, because you can go, this particular instance of JS94L is for the NASA Astrophoto Challenge. This is actually for the previous challenge, which was about the Carina Nebula and Eta Carina, which is within the Carina Nebula. This will give you a good idea of what the format is like for this particular tool, and then how to use all of the tools within it. So I'm going to click out of this Astrophoto Challenge, but if you clicked on Start Guided Tour, it would show you how to use most of the tools that are within here. So I'm going to X out of that. If you miss anything, you can replay the guided tour, or you could do the video tutorials. They also have written tutorials, so if you learn better that way, you can look at those. So I'm just going to quickly go over some of the material, and then I'm going to tag team with Madi so we can get a good idea of how to use this tool. So the first tab that we have is called Challenge Images. This is just a curated list. This is what makes it specific to the NASA Astrophoto Challenge. This is a curated list of images about the Carina Nebula, or Eta Carina, that NASA has come up with, both from space telescopes like Spitzer or Chandra or Hubble, and from ground-based telescopes like the Micro Observatory. So the Micro Observatory is actually a really great resource also, where you can go and request images of something in the night sky. I think they actually have representation on both the northern and southern hemispheres. So you'd be able to see most of the sky, I think. So you can go and you can request your own images. You can request different filters at different exposure lengths. And this is a really great tool for classrooms and for outreach as well. So if you're working with an astronomy club or if you're working with a classroom, I think this is a really cool tool. Right, so we have our challenge images, but we can also get images from other things too. We can open up other images in here as well. And there's a number of different places to get those from. Mari introduced a couple. I'm just going to point out a couple more. So there's also the Chandra photo album, which is another curated list. What's great about this list, it's not a ton of images, but it does have a bunch of really great, interesting objects to look at. These images that you can download, they're all photometrically and spatially calibrated, and they're all aligned. So that means if you remember maybe one of Mari's slides had MIRI images that were kind of like offset from each other, and they had to be offset because they were shifted when the image was taken, and then they were aligned so that, you know, all of the stars looked like they were in the right place, and all of the features looked like they were in the right place. And so you want those images to be aligned. It's really helpful if they're already aligned when you download the data, but that's not necessarily going to be the case, particularly if you use the database called MAST that Madi was talking about. And this is where astronomers go to find data that is from space telescopes if they want to use it in their own research. So you would go to the advanced search button. You would, in the mission, put in JWST, just because I think JWST is interesting. And then you would place maybe your object name. It usually requires the scientific designation of the object name. So like what its name is in a given catalog. So in the Messier catalog, the Eagle Nebula is called M16, and that's what I've put in here. So then I have my mission, I have my object name, and I could click search, and I get 13 records, which will show here. And then what's kind of cool is that on the right-hand side, you can actually see where all the fields of view are for each of the individual images. So if you click on an image, or if you click on the rectangle on the, say you click here, you can see which FITS image corresponds to that particular chunk of the sky. I think that's a neat feature. It's certainly helpful when you're if there's a crowded field, or if you're trying to look for a very particular part of the sky that you want to investigate. So you would download this by clicking this floppy disk button. You would download a zipped folder. You'd uncompress that, and then you can navigate through that. And I'll actually show you an example of that in just a little bit. So we can go to our challenge images just for the sake of ease, and we can open up actually as many of these images as we want. It doesn't really matter. It might take a little while to load. That would maybe be the only limitation, but you can actually open up all of these images at once if you wanted. And then you would click on them to open them, and then go to My List, and it would show you which ones are open. Yes, and it's still thinking about it, which is why it's taking a little bit longer. So I have 5 images open, and you can see the one that's in the foreground that I can edit, and that when I scroll my mouse over, we have changing values for the location of my cursor and the pixel value, which you can also see in under the information tab here as well. So the one that's highlighted in green, the file that's highlighted in green is the one that's in the foreground. That's the one that you can edit in that particular moment. If you can't see the difference between green and blue, which many people can't, you can also see which image is displayed by this entry here. So Edekrina, Chandra, X-rays, low energy FITS. So that tells me what I'm looking at specifically. So if I decide I have too many things open, I want to close some of them, I would just click on this. It looks like a gray rectangle in my my version. I think there should be a little X through the gray rectangle, but if I click on that, then it would close that image for me. And I can close all of them if I so choose. But I can also go here and click close image. Oh, that's weird. Maybe I shouldn't do that. Okay, I will just continue to click on these gray rectangles and it'll close it for me eventually. Maybe it doesn't want to. There we go. Okay, so now I have a completely blank slate once again. I could go to the image tab and I can actually open my own image. So I'm going to do that. I click open. It brings up this dialog box. I'm actually going to go back to where I downloaded all of the zipped information from MAST. You can see I downloaded 3 FITS images that came to me as zipped folders. You can double click on that and it'll unzip it for you automatically if you're in a Mac. I'm not entirely sure how it works for PC, but I think it's probably pretty similar. And you can also do that from the terminal pretty easily as well. But I'm going to click on one of these unzipped folders. You navigate your way through it. Where your image actually lies is within the folder that corresponds to the filter that you downloaded. So this filter was F770 wide. So I'm going to click on this, and then my image file, my actual image file, there's a couple images in here, is the one that ends with _i2d.fits. And so I'm going to click on that and open it. And it will open this beautiful image of M16 that I've downloaded. So the next tab over is our tools tab, and there's a bunch of different things in here, and I really would encourage you to explore and just see what each of these things does. For instance, all of these image filters can be pretty fun and can bring out some of the features that you might want to look at, but they don't necessarily say anything like scientifically, but it does. It doesn't necessarily have to be a scientific choice that you make when you're creating these images. But some tools that I think are really helpful for you will be the shift. So if I click shift, you remember what I was saying about the alignment of the images. This is when shift becomes very useful. So shift is great because if you click on that button, it'll bring up this little box that has 4 arrows, and maybe kind of intuitively you could guess that if you click on these arrows, it'll move the image in one way or another. This is really important because you can't always use this auto align images tool. This auto align images tool really only works for the challenge images when you have NASA data. It does not work for micro observatory data, unfortunately. I think it has something to do with the way that it's processed. And it won't work for, oh, I've got an open one now. And it won't work for data that you download from MAST. But it is a really useful tool for the NASA data, at least. And then blending, I'm going to get into a little bit later, but that is also a tool that I think you'll probably be using. Of course, we have zoom. You can zoom in and you can zoom out to see the full image. Maybe zoom in again. And then you can change the scale. So I think Mari is going to talk a little bit about the scale, but basically what this does is it applies a function like a logarithmic function or an hyperbolic inverse sine function to your image so that you can see features a little bit better than you could before, sometimes a lot better than you could before. And then different functions will allow you to see different things. So like the regular hyperbolic sine doesn't really help us that much with this particular setting, but a square root function has a very different view. So the scale gives you a different way to look at your data and a different way to normalize it, I should say. So I'm going to send it over to Mari, who's going to give you a good look at how you can use these controls here below.
Thank you, Kelly. So yeah, so basically I have the same image that Kelly was working on, and it's now rotated 90 degrees to the left, and we want to adjust the different level of luminosity in different tonality to extract the most details from the image. The first thing we do is, of course, set the upper level here, the low brightness limit. This is basically sets where the black point of the image should be set. You can see it if you go higher up, it will put the black point of the image in much higher than what it should be. And if you come down, you are putting the black point lower. So how to set the black point? The first thing to consider is that where is the data? Can you see the data in the image? For instance, here it's clear that, for instance, the data is in this part of the image, and a bit here, and these black parts are actually part of the instrument outer parts that were not sensors, and these are not, there is no data captured here. And there are some smaller black parts in here that also missing data. So we wouldn't actually set the black level or low brightness limit based on these parts. We would set it based on the first pixels turning black in the data part of the image. So for instance, if we can now zoom in here. So I just want to set it a bit higher where I can see the first blacks in my image. You see, these are very darker, dusty areas. Okay. It's a bit too much. You should stop where you feel that you're losing data. What I mean by losing data, I mean you see the details in the darker tones are gone because you set the black too high. So you could also put it on 0, probably for most of the images, but then you have to change the overall contrast of the image and colorize. So I suggest to change it here a bit. The second thing would be to set the highlights or high brightness limit, or the what I like to call the white level. So you would basically tell what part of the histogram can be read as white. And if you go too much to the left, you see that lots of details are gone in the brighter parts because you set the white level too low. If you go, as you go higher, you see the details are recovering, and these are parts that you can now see the details of. But you have to be careful. If you go too high, you see that even the stars are not really bright enough anymore. Sometimes even the fainter stars even become dark gray, like the ones in the background. So I would say stars, especially bright stars, are could be very helpful to decide which where it should be set the white level or the high brightness level, which based on the stars and the details in the nebula I set it to here for this image. The other thing that we do next is to set the scale or how we read the histogram. And the most basic one is linear, of course, and then there's a logarithmic, arcsine edge, sin edge, and square roots. The most common ones that we used for images that are rather dark, like this one, is arcsine edge. And if it needs to be more stretched, sometimes square root, and but this is for images that are have some considerable dark areas included. If you are working on image that is taken from bright nebula, or there is a bright source of light covering more than 20% of the image total area, then I would suggest using something like logarithmic and linear. Or if the depth of the sensor that the image was taken with is not really high enough, and the sensor is not modern CCD or other digital sensors, then you might not have enough possibility to stretch the histogram so much. So you might want to go back to linear, or linear probably most likely. And okay, so we set it for this image to arcsine edge, and then here we can set the stretch of contrast. This is basically what, for instance, in photography or in other fields related to images, are considered as color gamut. And this is typically set to 1.1 or 1.2. This depends on two things. This depends on the colors, the color profile of your display, which is often sRGB. So it's best to put it on 1.1 because gamut of sRGB is 1.1. And also how you in what color space you want to create this image. And this also stretches the number of grays in your image. For instance, you see as you come here, lower here, you have much more gray. After you go higher, you have more black and white than grays. So 1.1 is usually my recommendation. If you're using a 16-bit display, or if you want to use a 16-bit image, you can go even lower. And if you have problem with the contrast, you think it's too low, you could go higher. This I would set it to 1.1, and then there is the shift of a gray gradient. So you this is called shift bias. This is basically where you want to set your midtones, where you want to set your middle gray. And the lower you come, the less black you have. The higher you go, the less white you have. usually somewhere in between, but for astronomical images, a bit toward black, so we will have more gray and we could extract more details in the colorizing. Okay, that was my part. Hope it was helpful. Back to Kelly.
Thank you. Thank you. Thank you for that, Maddie. So I'm going to pick up where he left off, and we're just going to quickly talk about the finishing touches on your images. So I have an image. I want to keep it like this because I think it's fun to look at things upside down sometimes. Or what is orientation in space anyway? Good question. So we can go to this next tab, color. And right now I have it on the gray color map, but I could invert that color map if I wanted to. So right now the dark ones correspond, or the dark spaces correspond to less light, and the lighter, whiter spaces correspond to more light, but I could invert that very easily. And maybe it would look kind of funny to us because our eyes are, and our brains are used to seeing things that are, where darkness corresponds to less light, and lightness corresponds to more light. So maybe this is kind of jarring for people to look at, but for seeing things in new ways allows us to see more detail, maybe in ways that we didn't perceive before. And that's kind of the whole point of colorizing things in different ways to bring out different features that you might want to accentuate. So I'm going to bring it back to the color map that we're used to. And you can choose to colorize this in whatever way you would like to. I happen to really like these, the Viridis, Magma, Inferno, and Plasma. I think they're really cool, and they have a nice way of distributing the color that makes it easy for our eyes to see, particularly if we're not sensitive to all these colors. So I can choose one. And I think that it makes the image look cool. I think what's important when you're playing around with this is to find a color scheme and a scale and a set of controls that just feel good to you and look good to you. Finding something that or trying to extract something out of the data that isn't necessarily there can be really strenuous. So I would just encourage you all to really play around with this and try to find a maybe this really speaks to you in some way, and that's important too. It's not necessarily all about the science, and it's not always all about what other people find aesthetically pleasing. It's what's aesthetically pleasing to you, and creating an image that you think is nice. So I'm going to go back to, let's go with Plasma. I think Plasma is nice. And you would repeat this for all of your images. So you'd go back to your My List. I've loaded in 3 different filters, and you can choose any one of these. Oh, I should say, before I move on, Maddie talked a little bit about the chromatic order. So if you have red, green, and blue images, and you want to combine them to create what we would maybe call like a true color image. And you could do that with these challenge images, with the micro observatory images. And if you did do that, you would go through the same process and then colorize each image based on the filter that it was taken with. So you would colorize this one with the red color map, this one with the green color map, and then the final one with the blue color map. And those are just red, green, and blue right here. And then once you've done all that, you would click on this RGB mode button. I'm not going to do that right now because I haven't created those images and it would give me an error. So I'm just going to leave it for now. But if you decide that you want to create your RGB image, then you would go through that process and click on this button, and then it would combine those images for you automatically. But if we're not doing that, if we're just creating a multicolor image with various different color maps, then we can go back to our tools. And I promised I would talk about blending. So we can click on this, it'll bring up another dialog box, and it gives us a bunch of options. So I'm going to click on image blending. So it's going to bring all of the images that I've created onto one kind of layer, so to speak. And I can blend using a number of different formats. I can blend, then they're all listed here. I think really what you should just do is go through this and try to find blending techniques that you think are interesting. They don't all necessarily have to be the same. They could be different, and then you can change the opacity. That's this other little drop-down menu. So you can change how opaque a given layer is, and then you can change the kind of blending that you choose to use. So you just play around with this and try to figure out something that, again, looks pleasing to you and is interesting to you and is bringing out the features that you really want to see. So there are two more tabs on this menu bar, region and analysis. They are not useful for creating images, but they are useful if you want to do science with your data. So you can put down a region. So you click on a circle region maybe, and it'll plop that down here. You can change its size. You can change its location. And then you can go to analysis and click on any one of these, and it will give you an analysis based on what pixels are within that region. So it's a really cool way to do some science with the data that you've actually, with the image that you've created. But again, it's not necessarily useful for creating multicolor images. So I'm just going to delete that. And you just delete it pressing the delete button. Okay, so that is the extent of the quick tutorial to JS94L. I hope that was useful. If Susanna, could you put in the chat the link to the overview of everything that I went over? Thank you. So you have access to the basically everything that I just said, in addition to all of the tools that I think are the most helpful for making your multicolor image. I go step by step to help you through the process of creating your own image. And then I have a list of all of the resources, like I promised Mita-san, for you to not only get your own images from MAST or from Chandra or from Micro Observatory, but also to find images that have already been created, and then a bunch of different programs that you can use. So this is not the only program that you can use. JS94L is not the only one. As I said before, there's DS9 and JS9, which are two different variants of JS94L. There's the number of different programs that were listed by Madi during his presentation. And then there's also Makali'i, which is a program that's kind of similar to this, that's only for Subaru data. So you have the opportunity to explore that data as well, which is a kind of a fun thing, particularly here in Japan. So I am going to move to a different screen. Is this the one that? Yes, it is. Okay. And I'm going to put up these questions again. So I put these questions, if you all can stay, which I hope you can, I'd like to have a just brief discussion about how you can bring these resources into your own communities. And some things that I want you to think about. I sent these in an email to everybody that signed up about 72 hours ago, or at least more distant than 72 hours ago. If you signed up within that period of time, I'm sorry you didn't get this email. But what I'd like you to do is to first, in maybe 2 or 3 minutes, think on your own about these questions. And I know it's a lot, but it's probably something that you've already thought of already, and you just haven't maybe put it in this context yet. So what is your goal in doing outreach, either personal or institutional? And how would you know if you were making progress toward that goal? So how would you evaluate yourself or the work that you do in order to know that you're achieving your goals? What audience do you need to reach out to in order to achieve your goal? So instead of thinking of the audience first and then thinking about what you want to do, I'm asking you to think about your goal first, your own personal or institutional goal, and then saying, okay, now that I have this in my mind, what audience do I need to work with in order to achieve those goals? And then you need to know something about the audience, right? You need to know what they know about the topic. And you need to know what you could know to help them figure out more about the topic. And then it's good to understand your own motivations. Are you trying to influence a behavior or attitude? So for instance, are you trying to get people to recognize the importance of images in scientific exploration? Or are you trying to get students who are more inclined toward art to appreciate and like science, and to bring them into STEM careers in some way? So we'll take 2 minutes, just think about those on your own. And then we'll have this discussion together. What activities could we design around image processing that would align with your outreach goals? Okay, so let's spend the next maybe 10 minutes, if we can get there, talking about this question. What activities could you design around image processing that would align with your outreach goals? I'm going to stop sharing my screen because I think it's important that we look at each other when we talk. So I invite you to turn on your video if you feel comfortable. If not, that's fine too. But so does anybody have any ideas that they want to share in the beginning? Yes, you need to.
Okay. Okay, so I am Tomita from Japan. I am the staff of the teacher training faculty, university staff. So I want to convey school teachers and students that a lot of work goes on into just one image they see in the newspaper or on TV. So students and teachers would think that, wow, it's a great picture. So please give us much more images. Okay, we need a lot of work to process just one image. So I want to convey this great effort scientists and technical staff and outreach practitioner is making. So this is what I want to convey to school teachers and students.
Okay. Well, you certainly got a lot of material today.
And very much thank you for that, because that's actually something in ESA, as a member of public outreach team for web, we've been struggling with people asking us, okay, today image was nice, what will be tomorrow image? And we're like, give us a break, please. And it's just let us. I think so far we're producing one image per week, but we're still under lots of pressure to produce much more. And this is just not about also image producing and all the work, which sometimes could be days of work for a single image that goes just for the post-processing of the image. It's also the science that needs to be done behind the scene, the science that needs to be then validated by the peers of that scientist. And this is a process that we want to make sure, because we just don't want to always just share a nice, beautiful image. We want to also share that, okay, see that a blob on that part of the image? That's something new. That's something we've never seen before. This is the science behind it. We now know something new because of this image. That's the story we want to highlight. So thank you for that.
So Tomita-san, what kind of activity do you think you could bring?
Yes, recently due to the COVID-19, so I haven't visited the local schools, but the next year, so I will be able to visit the local schools to meet many students and teachers. So I would like to do this kind of image and colorizing activity with the students and the teachers, and enjoy how to make just one image with a great effort. And of course, after processing the image, so we can extract the physics and astronomy that exist behind the image. So not just admiring the image. Wow, so the photo are very beautiful. Yes, it's very beautiful, but it also contains a lot of science. So the science is also very beautiful to our mind. So I would like to convey the great effort to make image and also the science behind the image. So I would like to visit the local schools in near future. So far in Japan, many school teachers are very nervous about the school visiting, but I hope at least the next year I would like to visit many local schools.
Is it possible to do like a virtual visit? Because all of this stuff is online. So can you meet with them over Zoom? Would that make the teachers feel better?
Yes. Maybe I hope so. So, but so far I don't know the present status at schools. But so anyway, so some teachers are very optimistic about this kind of activity, but others are not so optimistic. But anyway, so I will see if there is a chance for this kind of workshop at school.
That's great. That's really great. And if you do that, feel free to share the document that I provided if it's helpful. If not, then that's fine too. Does anybody else have any idea about how they might bring this to their people, whoever they may be? Mari, you actually were in a group yesterday with, or in your case earlier today, with a couple of people who were talking about low-cost ways to bring this activity or to create a low-cost activity around image processing. Do you remember that? Do you want to talk about that a little bit?
Yeah, so basically what we were discussing was that how we can bring kind of possibility to play around with these image processing and datasets to a more maybe underprivileged societies, or also some kids that maybe should not really interact too much with digital devices, and like, for instance, kids under 8 years old. And what was suggested was that every educator could, of course, use this information to process the web image for themselves as they want to see, but they can also produce single color images for each filter and then print those together with the final colorful image. Put it in front of the kids, put it in front of people that we want to communicate better with, and they can show it to them one by one. For instance, what features do you see in this image, the blue filter? What part of the image are different in the green filter? What part are different in the red filter? And then you would put down the colorful image, and then you ask them, okay, now what is new? What is new in this image that you didn't see in any of those previous images? That help them to both understand the process, how those green, blue, and red become that colorful image, and as well as seeing better, seeing some features in astronomical objects better, especially those that might be very faint in specific wavelengths but once they're stacked together, different wavelengths of light are stacked together, they become much more noticeable because the contrast is higher, the color contrast is higher.
That's a really cool activity, I think, because it, it brings a lot of this stuff that can be really technical. It makes it tangible. I think that's a great way to bring in more people and to make it a little bit more inclusive.
And I think that's also includes some of the basics that we do science with the images, right? We want to know exactly what feature in the object is different in what filter. And so we could add also a bit of science depending on the age of the people that are being presented to. For instance, yes, this is sulfur, this is oxygen, ionized oxygen, this is how ionization works. This is the same oxygen you breathe, but in a different formula and in a gas cloud far away. And then you can also discuss, for instance, in matter of James Webb images, we have lots of now deep field images that actually that may not be yet public knowledge, but there are very nice deep images that will become public in the next few months of several parts of the sky. That these are deep exposures. These are dozens of hours of observation by James Webb, and they are meant to for us to see the galaxies in the early universe in a few 100 million years, a couple of 100 million years after the Big Bang. And these are some of the, these are some of the furthest points away that we've ever observed, and these will also represent a kind of a time machine, right? We're looking back through the time as well as we're looking far, far away. So we have lots of filters for some of these fields. I think we have up to 11 or 12 filters. And as you go through those filters, as you go toward further toward the mid-infrared or further to the red color, if you assign in chromatic order, the ones closer to optical light would be blue, the ones closer to mid-infrared would be red. So if you color assign those in that order, as you go toward that red, the galaxies that are further away would be more noticeable. So you see, for instance, a galaxy that is visible at 900 nanometers or 1200 nanometers or 1500 nanometers, but it fades away. It stays steady because it's closer to us. But then something becomes visible, starts to become visible as you go through the mid-infrared. And that something is a galaxy much, much farther away with a big redshift that was pushed all the way toward the end of near infrared and early mid infrared. And that's excitement to find that point. Could be to find those points, because those points are the early galaxies in the universe, first point that we've ever observed. And how to find them is exactly like that. So we could print all the 12 filters, color assign all the 12 filters, print those filters and put them one by one in front of the audience. And they can, for instance, try to find the source of lights in the next image that was not in the previous one. as they go forward, they notice there are some galaxies that they're finding that are actually further away from them, and they're actually looking back at the time. And that could be the final surprise for them.
That process of like looking at different images of different, or looking at an image of an object in different filters to see where objects appear and where they disappear reminds me a lot of identifying, or how they used to identify like transient objects in the night sky from looking at photographic plates. Yeah.
Especially since these are broadband filters, there are not narrowband filters designed just to see a specific emission band. These are broadband filters, so and they were taken from a very large area of the sky compared to the normal field of view of the web, and they are all galaxies or stars, so they all have emission in different part of the spectrum. It's not like a nebula that you can see a lot of structures in one part of the spectrum and completely different structure in another part of the spectrum. So you will notice the gradual change of the luminosity as the filters changes.
One question is okay. So you mentioned about the astrophoto challenge. So if my memory is right, so is there a deadline to submit the images? If the deadline is not so close, so I'm now thinking about making the manual for beginners in Japanese for Japanese colleagues. So I think we can write several kinds of manuals for beginners about the data processing, the colorizing processing, and the astrophysics about the dust distribution in nebula, astrophysics about the redshift of the galaxies, astrophysics about the very distant galaxies. Okay, so we can make the different kinds of manuals for the non-STEM high school students, manuals for the STEM course students, and for undergraduate students, and for public general public. But we need some time to prepare because I and my colleague want to write that kind of manuals. Very happy to do, but we still have some time to do that. So if the Astro Challenge deadline is very close, okay, so regardless of the deadline, so we can prepare that kind of manuals and spread the manuals to the local community, and various kind of people can enter the world of the image processing and the colorizing processing to use that in education field or other outreach. Okay, so my question is that is the deadline of the Astrophoto Challenge very close?
So the JS94L instance of the for the Astrophoto Challenge that's coming up will be released on January 2nd. And then the challenge will end on February 28th.
Okay.
So it's kind of close.
Okay. So if some students and some teachers and some people in local community can make it to the deadline, so they're very happy to participate in the challenge. And if not, it is still okay, because many people can learn how to process and how to colorize the image, how to extract the science and astronomy from the images. So so we have two goals. One goal is to submit the Astrophoto Challenge, and a second goal is to have the manuals and the create a new community to enjoy the image processing. Okay.
Yeah, absolutely. And I think that's an important point that, I'm putting this all within the framework of the Astrophoto Challenge, but it doesn't necessarily need to be that way. Or it goes so much further beyond just the Astrophoto Challenge, that if you learn how to create these images for yourself, then that's something that you can then go on and continue to do and bring to other people as well. So I think it's a worthy dual purpose for sure.
Okay.
Does anybody really quickly want to just talk about something that they mentioned that they thought was interesting?
We don't know what this was talking about, but Mahdi gave some good ideas about bringing out low-cost ways of doing the same thing with maybe printouts rather than having needing a computer. Low-cost and low resource ways. So and asking people to look at the different already processed images in different filters, etc., and then giving them a complete overlaid image and see what kinds of details there are possible to see in each separately, and then can they be seen in the final image, or can they see something better in the final image?
That's really cool. I like that a lot. Yeah, that's a really great idea.
And hello, maybe I say some words for the case in China. Yes, and also because now in China, I'm the chief editor of our amateur astronomer magazine. So the magazine we have nearly 2,000 readers. Yeah, but so not reader. We publish nearly 20,000 issues every month. So I think maybe I can write something about this project but for my end, so I need to get some accurate information, because based on my understanding, maybe I'm not so clear about the details. So maybe if there is anything, some written things about this, so I can translate, and then I can write something. So write something there. So because our magazine also read not only for amateur. I think most Chinese amateur will read our magazine, but also there are many professional astronomers also our readers. So based on what I saw today, I think it's very, very interesting. And also someone posted the observation schedule, the currently observation schedule of JWST. So I think all this information, if it could be available, and maybe many professional astronomers also very interested in this. So yeah, just I want to find some accurate information by reading, not but because my here is not so completely. Yeah.
Yeah, of course. Well, I'd be happy to answer whatever questions you have later on. We're also going to send around all of the resources that we put together, including the presentations, for everybody to look through and enjoy on their own time. And I'll send that probably in the next couple of weeks. So you'll have all of that information, as well as some of the information that I'm going to show in just the next bit. So I think what I'm going to do now is
sorry, another question. You'll be sharing the recording, right? Because I missed the beginning part of the session. Yeah.
Yes, I will. The recordings, the presentations, the document that I shared, and then the questions that I posed to the email that I sent out yesterday. And if you signed up for this workshop within the last 24 hours, you didn't get that email. So don't worry if you don't know what I'm talking about. I'll send all of that in another email to the full list of people who registered for the event in the next couple of weeks, so that you'll have all of that. So I want to just wrap up really quickly here. Okay, so we had a ton of resources that were discussed today. These are all in that PDF or the Google Doc that Susanna put in the chat a little while ago. So don't worry about getting all of these links back. but just know that all of this information is in there for you already. We've collated it from both presentations today. On the horizon, something to look forward to. Of course, we have the NASA Astrophoto Challenge that'll open on the 2nd of January and close at the end of February. So plan your events accordingly, whatever it is you would like to do with this challenge, even if it's just doing it for yourself, plan accordingly. We'll then actually have a follow-up workshop on accessible images in mid-January, probably on January 17th. The whole purpose of this is to take the images that you make using JS94L, as you've just learned how to do, and then bring them to this workshop on accessible images and think about your choices and the image that you've created in a way that is accessible for people with blindness and visual impairments. So that's going to include these image descriptions, but it'll also talk about tactile models and sonifications and other ways that you can make your images accessible. And that's going to be with our own, I don't know if he's still on here, but Cesare Pagano, and then also Kim Arcand from Chandra will be joining us, and some of her colleagues who work on accessible images as well. So please be sure to bring the images that you've created to this workshop. Keep an eye out for a sign up for this, and it'll be similar. We'll have 2 sessions, one maybe in the evening, one in the morning in some time zone. And then, yes, so please keep an eye out for that. Okay, and there we are. That's it. We are a half hour over time, and I'm so very sorry about that. I'm sorry we didn't have more time to hear about the different ways that you're going to bring this into your communities, but hopefully this is a good place to start. And I hope to see you in January. So keep an eye out for an email from me with all of the different resources that are available to you. And I will leave it as that. Thank you so much for being here.
Bye, everyone.